In this next video, we will look at the extension of the single neuron binary classifier to the multiclass case, swapping a sigmoid for the softmax function, and binary cross entropy for multiclass entropy. I'm not asking you to implement any of this, but the concept itself is important. In the process, I will introduce the concept of one-hot encoding for multiclass labels and review more activation functions, including those more commonly used today. This should be considered core content. So as indicated, softmax is an extension of logistic regression to multiple classes, and it achieves this through the softmax function given by the following equation. It takes a vector of real numbers, length k, representing each class, and normalizes it to a probability distribution of k probabilities which sum to 1. Multiclass entropy is then estimated using the following loss, which is an extension of the binary cross entropy expression summed over all classes. So the main change is that rather than having a single output neuron and one prediction per example, we'll now have k output neurons and return k probabilities for each of the k classes. This will change the weights matrix to now have shape k by m instead of 1 by m, and z will then have shape k by nt actually, where here I'm considering all examples, although this diagram is only showing output for one. Then f will also have shape k by nt, as z and f always have the same shape. So looking at the computation graph for the softmax function, the forward pass, as stated, looks different because now we have k output neurons, k estimations of z, and k softmax probabilities per input example, of course. And thus our final loss for each example is a multi-class cross entropy which considers each of the k possibilities. Note, to implement this, you will need to apply one-hot encoding. This is a concept that you will likely hear about often, not just in this course, but broadly in the context of deep learning, so it's worth taking time to make sure you're comfortable with it. The idea is simply to change the way we represent class labels from a single whole number to a vector encoding, where the length of the vector is equal to the number of classes, and the vector encodes a 1 at the index equal to the class, and zeros elsewhere. For example, here we have a choice of 3 classes labelled 0, 1 and 2. The one-hot encoded version of this is given on the right-hand side, where each example is represented by a length 3 vector. Then, for examples with class 0, the one-hot encoding is given by 1, 0, 0. For examples with class 1, the one-hot encoding is given by 0, 1, 0. And for examples with class 2, the one-hot encoding is given by 0, 0, 1. The purpose is to allow for the estimation of the multiclass cross-entropy loss using vectorization, where the true prediction will be 1 only for the true class and 0 everywhere else, whereas for the predicted classes we will return a probability for each. The objective, therefore, is to optimize the weight so as to push the predicted class label probabilities to as close as possible resemble the ground truth one-hot encoded ones. So now we're armed with everything we need to compute the backwards pass, remembering that this loss here represents a loss for a single example with the I notation dropped for simplicity. This is estimated by comparing the length k predicted labels with the length k one-hot encoded true labels for each class. Importantly, don't forget yk is only going to be 1 for the true label, so this reduces to a single term. We now need to estimate the gradient of the loss with respect to the parameters as we did for logistic regression, working backwards from the right-hand side. We start with the derivative of the multiclass entropy loss with respect to f. This is given by the following expression. As we know, the derivative of log f is 1 over f from our simple derivative rules. Next, the derivative of the softmax is given by the following function. Delta here is given by the Kronecker delta, which I will explain what it means in the next slide. Finally then, to get the loss with respect to the parameters, we can combine all these together with the chain rule. So we have the partial derivative of L with respect to fk, then the partial of fk with respect to zi, and finally adding the partial derivative of zi with respect to wi1. Because now w is a matrix, not a row vector. So we saw that this before was x. This is simplified to the following expression, which again I'll explain briefly in a minute. So we're going back to derivation of the partial derivatives of the softmax in brief. For those who are interested, differentiation of softmax is achieved using the quotient rule of differentiation, and this is explained in more detail in the linked source. However, looking through this is entirely optional. The main takeaway, however, should be that unlike logistic regression, we no longer have a single f and z, we have k of each. So when estimating our gradients, we instead need to consider all combinations of derivatives of f and z. These are partial derivatives of fk with respect to zi. It turns out when you work through all of these combinations, they reduce to two results. One for where the class is the same as z and f, so I equals k, and one for where class is not the same, so I is not equal to k. Further, this can be reduced to a single expression using what is known as the Kronecker delta. So this is written as the symbol delta ki, and it simply takes the value 1 if I equals k and 0 otherwise. So if I equals k, the expression reduces to the I equals k case because the delta becomes a 1. And if I doesn't equal k, then delta will equal 0 and the expression will reduce to minus fk fi. And again, very quickly explaining the simplification of the loss with respect to the parameters for those that are interested. This also manipulates the use of the Kronecker delta. So the first thing that we can do is cancel these f's. The next step is to first consider the case where k equals I and k is not equal to I separately. In the first case, delta will be 1, so we get yi times 1 minus fi. But in the second case, delta is 0, so it disappears. Then we can multiply this first term out. And once we've done that, we can bring this yi fi back into the sum, such that it again sums over k, including the case where k equals I. So you can see the change here. This means that we can get rid of this sum over all yk as it sums to 1. So this gives the reduced expression. Then the vectorized forms for all the components are as follows. So z equals wx as before. But now our w has one row for each class, so it's a matrix. One thing to note is that the softmax has the potential to be unstable due to the presence of exponent terms in the numerator and denominator, which can tend to infinity. So it's common practice to add the following term, where log c typically subtracts the max value to effectively normalize and prevent this from happening. So that's it for the explanation of softmax. These are the forwards and backwards class computations for reference and in NumPy. However, we will not ask you to code them up, but you should be able to see that they reduce more or less to what you saw before for logistic regression, allowing for one-hot encoding. So finally, let's talk a little bit about activation functions. So far, we've used the sigmoid function, but this can be problematic as it can lead to vanishing gradients as it saturates at 1. This is a problem because updates can become infinitesimally small, such that the algorithm ends up appearing to converge far before the optimal solution is found. Therefore, while sigmoid is still commonly used for the output prediction layer, it is now rarely used for hidden neurons. After sigmoid, the tan-h function was used for some time. This has some advantages because its output is centered at 0 and its derivatives are steeper within this intermediate range, but it still faces this saturation problem. Nowadays, people generally use the ReLU or its variants. This corresponds to the max function such that the function is 0 for negative inputs and it's linear for positive inputs. This is good because it doesn't saturate, so it avoids the vanishing gradient problem, leading to faster convergence. Also, its sparsity means that it can support more concise models, where by sparsity I mean that the neurons are non-zero only for a few inputs, and this can help avoid overfitting. It's not perfect, however, due to the dying ReLU effect, where neurons can get stuck on the negative side and always output 0, meaning that they don't contribute to the solution. To address this problem, teams came up with the leaky ReLU, which avoids this by adding a negative slope of very small gradient, for example 0.01. However, the specific value of the alpha parameter can be optimized. ReLU 6 is another modification which caps the function at 6. This can be advantageous as it avoids activations from exploding. and some experiments have shown that it further encourages the network to use sparse features. However, how is it that a piecewise linear ReLU function can learn non-linear functions? We've already said that we can't chain together linear functions to make a non-linear function. Combinations of linear functions are linear functions, so why is a ReLU different? The reason is that combinations of ReLUs generate non-linear step-type functions. For example, here is a combination of two ReLU functions that approximate a sigmoid. Hence, these functions can be combined as before and shown previously by the Martin-Nielsen example, which I linked to before. So that means that they are also universal approximators, and this bottom link gives a specific example of that for ReLUs. So here is a list of possible activation functions with their derivatives. As I've already said, you're still likely to see the sigmoid or softmax in the output layer of a classifier, but otherwise ReLUs or their variants are often used for the rest of the network. Finally, initialization of weights. This should be randomized, otherwise the network will not train. Why is this? Well, if all weights were initialized to the same value, i.e. 0, then the neurons of all layers will start by performing the exact same calculation, each returning the exact same output and therefore making the layering redundant. Thus, weights are initialized in a range of increasing sophisticated ways, but always to small random numbers, for example as shown here. Now we will come back to this in week 3 when we talk a bit more about improving the efficiency and accuracy of networks for medical image analysis. So in summary, for multi-class classification, the sigmoid function must be replaced by a softmax, which returns a probability of an input belonging to one of several classes. The associated loss is multi-class cross-entropy implemented using one-hot encoding. While sigmoids and softmax are often used in the output layer of a classifier, they are unsuited to training all neurons in the network due to the saturation at 0 and 1. This leads to vanishing gradients and very slow training. Thus today it's more common to see ReLU functions. Finally, don't forget that the weights of multi-layer networks cannot all be initialized to 0, else the network won't change. Instead, it is common practice to initialize to very small numbers. Before you go on to the next optional video on multi-layer network optimization, please complete the Keeks quiz.